In this lesson, I walk through how asymmetric encryption works, how it's managed with PKI, and how it's used to establish TLS connections. You can download the script for this video by clicking above or at the end of the lesson. One of the best ways to protect data at rest and in motion is via encryption. The two general types of encryption are symmetric and asymmetric. We take a high-level look into how these work in the next slides. Data at rest is usually encrypted via symmetric encryption. It is fast, which is needed when quick encryption and decryption is needed during business operation. It's also used in security internet connections like TLS and HTTPS after the key exchange takes place. This graphic shows how this works at a high level. A single shared key is used to both encrypt and decrypt information. Asymmetric encryption methodologies use key pairs. Each entity using asymmetric encryption is issued a public-private key pair. The most common way of doing this across an enterprise is with a public key infrastructure, or PKI. The sender of a file uses the public key of the recipient. Public keys are widely known, or they're kept in a public key directory. The recipient then uses its private key to decrypt the information. No one other than the recipient of a key pair should know the private key. A PKI, or public key infrastructure, is an asymmetric key management framework. It's a hierarchical trust solution that consists of four components: a certificate authority, a registration authority, subordinate CAs, and a mechanism to provide a central directory distribution management capability. This includes managing revocation lists. It uses programs, data formats, procedures, security policies, and public key cryptographic mechanisms. A certificate contains information about the entity to whom or which the cert is issued. In addition, the certificate is tamper-proof and can be traced back to the issuer, or the certificate authority. Traceback is needed for verification of the certificate when presented for holder authentication. The certificate contains a public key, a person's or organization's identity, and is signed by either a CA server or it is self-signed. It binds an identity to a public key. Self-signed certificates are not considered very safe because no third party verified the certificate signer's identity. There are different kinds of keys issued by the CA, including those that enable code signing, email encryption, digital signing, and secure internet connectivity. The certificate issuance process is simple, but takes some time if properly done. A CA root server is created to establish a PKI solution. The root server creates a key pair, and the private key is the root of trust across all issued certificates. The root server can be created by an organization to create an organizational level PKI, or an organization can subscribe to a CA service. Root servers should not interact directly with requesters. This isolation is needed to protect the CA's private key. As I show later, if the CA's private key is compromised, all issued certificates are essentially invalid. Consequently, CAs rely on subordinate CAs to process certificate requests and sign issued certificates. This enables the CA to either remove the CA root server from the network or shut it down completely. There can be more than one subordinate server, and each is issued a signing certificate by the CA server. The subordinate CAs use their certificates to sign certificates issued to other subordinate servers or to certificate requesters. If an organization subscribes to a CA service, a service-owned subordinate server might be placed on-premise. Registration authorities verify identity proofs provided by certificate requesters. They approve the issuance of certificates and have the certificates created by subordinate CAs. A person or organization sends a certificate request to a registration authority. The request content depends on how the CA verifies the requester's identity. Identity verification is critical for ensuring the certificate is issued to someone or something claiming a specific identity. Once the registration authority verifies the requester's identity, it issues the requester's certificate that contains the requester's public key. The requester is also issued a private key. If the key pair is generated on the requester's system, it is secured immediately after. If the private key is generated at the CA site, the private key must be securely sent to the requester. Certificates enable entities to trust each other regardless of location or whether human or technology. Adam has a certificate issued by the Certificate Authority A in our example. Hannah also trusts CAA. Because of the trust, Hannah will trust Adam when he presents his certificate and she validates it. TLS, or Transport Level Security, is a protocol used to secure Internet and other communications. It relies on the use of certificates to enable clients to verify the identity of resources and establish secure session keys. The sole purpose of TLS is to create a set of symmetric keys for secure communication. This is an example of how TLS versions prior to 1.3 work. It's recommended that all organizations move to version 1.3. The TLS process is a handshake between the client and the server. In general, the handshake determines which version of TLS will be used for the session, which Cipher Suites will be used, I cover these in a later slide, authentication of the server, and creation of server keys. The session keys are used for symmetric encryption of anything exchanged between the two devices after the handshake takes place. Before the TLS handshake begins, the client sends a SYN packet to the server. This is a session establishment request. The server responds with a SYN ACK to tell the client to go ahead. In step 1 of the TLS handshake, the client acknowledges the SYN ACK and sends a hello message to the server. The client hello message includes the TLS version and the Cipher Suites the client supports, and a string of random bytes. The random bytes are known as the client random. The server returns a hello message with the TLS certificate and the Cipher Suite it selected. It also sends a server random. The client verifies the validity of the server certificate. The client sends a second set of random bytes encrypted with the public key included in the server certificate. This encrypted client random is known as the pre-master secret. The server uses its private key to decrypt the pre-master secret. Both client and server generate session keys from the client random, the server random, and the pre-master secret. The client sends a finished message encrypted with a session key. The server sends a finished message encrypted with the session key. Communication between the client and server is established using the session keys for symmetric encryption of the traffic. The ephemeral Diffie-Hellmann, or DH, Key Exchange Algorithm also enables the establishment of secure connections. It's very similar to the RSA algorithm, with one significant difference. The server creates a digital signature with its private key that includes the server random and a DH parameter used to create the session key. Also, Diffie-Hellmann is the only supported exchange algorithm suite supported by TLS 1.3. After the SYN and SYN ACK process, the client sends a client hello message to the server that contains the TLS version and Cipher Suites it supports, as well as the client random. The server returns a message to the client that contains the server certificate, the server random, and the chosen Cipher Suite. Unlike the RSA TLS handshake, the server also creates a digital signature containing the server random and a DH parameter. The signature is encrypted with the server's private key. The client decrypts the server's signature with the server's public key. This validates the server's identity. The client sends its own DH parameter to the server. The server and client calculate session keys based on the pre-master secrets. The client and server send finished messages to each other, and a secure session is established. A cipher suite is a set of cryptographic algorithms used for TLS asymmetric key exchange, symmetric encryption for session traffic, digital signatures, and hashing, which is used for data integrity checking. At a high level, the only session cipher suites available in TLS 1.3 are AES as a block cipher and ChaCha20 as a stream cipher. Other ciphers like DES, Triple Des, and IDEA were removed from TLS with TLS 1.3. The TLS 1.3 handshake is faster and more secure. After the initial TCP SYN-ACK process, the client sends a client hello message to the server. That includes the client random using the key exchange cipher suite it guesses the server is using and the list of cipher suites it supports. If the client guesses the cipher suite correctly, the handshake continues. If not, the server sends a message that tells the client what cipher suite, including key exchange algorithm, it will use. If the client and server cannot agree on a cipher suite, the session is aborted. The server responds with its choice for TLS version, in this case 1.3, the selected cipher suite, the server's digital signature, and the server random encrypted with its private key. The client reveals the server's random value and verifies the client certificate. At this point, the client and server have exchanged everything they need to create the session keys. The server and client send finished messages by initiating a session. Asymmetric encryption is slower than symmetric encryption. Consequently, it's not often used for encrypting data at rest or for system-to-system secure connections. It's most often used for user-device process authentication, data integrity verification, and exchanging keys. While symmetric encryption is resistant to quantum computing, current asymmetric encryption approaches will not survive when quantum computing reaches acceptable performance and stability levels. Well, that's it for this lesson. If you have questions, please ask. And until next time, be careful what you click.